All right, welcome back. And so last video lecture, we went over deactivators. And so now we're just going to kind of summarize everything here. And so, when we went over activators, we went over the the alkyl group and the methoxy group. And so now we're going to kind of add to that list. And so what we find here is that we can characterize things as being strong activators or moderate activators. So things that are strong activators are things like where you have an oxygen attached to the aromatic ring or a nitrogen attached to the aromatic ring. So these are strong activators. And it turns out, just to let you know, that the nitrogen is actually that these things right here, that these compounds right here are the strongest activators versus the oxygen. And the reason is nitrogen's less electronegative, so these lone pairs are more able to kind of resonate into the aromatic ring. So these are strong activators. Now we start decreasing the activating ability of the atom as we start putting an electron withdrawing group attached to the oxygen or the nitrogen or an alkyl group. So again, these are moderate activators. Out of these four, this is going to be the most activating out of these four. This carbonyl is kind of going to be trying to pull electrons. So these electrons are kind of tugging back and forth. But because there's still the atom here, because the atom attached to the aromatic ring has a lone pair on it, these electrons are still going to resonate into the aromatic ring. And then we have things that are weak activators, and these would be the alkyl groups. The alkyl groups are by far the weakest of the activators. And then we have the deactivators. The strongest deactivators are the nitro group. It's where you have the ammonium, the ammonium salt, or you have three halogens on a carbon here. Now notice that in any of these cases and in all of these cases here, the one commonality between all of these deactivators, right, is the fact that the atom, when you draw, and just to remind you, the resonance structure of the nitro group looks like this. So just remember, the resonance structure of the nitro group actually looks like this when you draw the nitro group. So this nitrogen doesn't have any lone pairs on it. So when this atom doesn't have any lone pairs, so carbonyl attached to the aromatic ring, none of these atoms attached to the aromatic ring have lone pairs on them. And so then they're all electron withdrawing via induction. And some of these are also electron withdrawing via resonance. So for example, when I have the carbonyl here, I can move these pair of electrons over and move this up. And that's going to give me, I can show you that's going to kind of show you how those electrons are kind of moving or resonating toward that carbonyl here. And you see, because I'm putting a positive charge in the aromatic ring, it makes that aromatic ring less reactive toward nucleophilic or for nucleophilic attack. And then we have the weak deactivators. And so these would be the halogens here. So if I'm going to kind of rank these, and if I'm going to kind of make an overall list, and so maybe you could try to do that. So what would be good for you to do right now before I do it is to try to take all of those things and make your own list. I'm sure your book has it, and there are things online. But maybe take a minute and try to rank those things from strongest activator to strongest deactivator. Okay, so welcome back. And so what we have, if I'm going to start ranking these from strongest activator to strongest deactivator, so the nitrogen compounds where I have the amine, those are the strongest activators, followed by the oxygenated compounds where I have oxygen attached here. Okay, and then after that, we start having the amides, right? And then we have, after that, we have the esters, where the oxygen is attached to the aromatic ring. And then we have the alkyl groups. Then we have the halogens. And the halogens are really the tipping point. So these are all activators, and then once you get to the halogens, you get into the deactivating range, right? And then after here, so what's going to be less or slightly more deactivating than the halogens are going to be these groups right here. So any of these groups are going to be the most deactivating, and then the strongest deactivating are the nitro groups here. Okay, and remember, the halides are the only deactivating groups that are ortho para directors, right? So when you have this, so when you have that listing, if you go back and you look, these groups are the only things, the halides are the only things that are both deactivating and ortho para directors, okay? And there's a table in your book, table 18.1, that summarizes all of this, okay? So basically, so we have like oxygen attached to the aromatic ring, alkyl groups, nitrogen attached to the aromatic rings. Those are all activators. All activators, so if you kind of are summarizing this, right? Right? If something's an activator, that thing is also an ortho para director, okay? If something's a deactivator, it's most likely most deactivators are meta directors. The exception, right? The exception is the exception are halogens. Halogens are deactivating, but they're ortho para directing. All right, so look at table 18.1, and to be honest, it's important that you understand what makes something an activator or a deactivator, what makes something an ortho para director versus a meta director. But what's going to be the most useful for you is if you kind of memorize or start to incorporate the memorization of table 18.1, so that when you see a monosubstituted aromatic ring, you can start to think about like, oh, what's the product of that second electrophilic aromatic substitution? Is that second thing going to go ortho, meta, or para based on the directing ability of the group? All right, thanks. Let me know if you have any questions, and I hope that made sense. Or I hope that made sense. Let me know if you have any questions. Have a great day.